All right, so today we're going to talk about statistical interpretation of entropy. Um, there are some things we still don't quite understand in science. Some things that we can't mathematically predict, so we make approximations pretty well, and then also we can use statistical interpretation. In other words, we describe the probabilities of something occurring, and then we focus on the things that are most probable. So we're going to kind of talk about flipping a coin. And so when you flip a coin, in general, when you have a penny, you have heads or tails, right? So this is heads, and then we'll do tails. Actually, this is a better image. So when I flip a coin, I have two outcomes. One is heads, and one is tails. And we always in statistics we always start with this because it's simple and easy to keep track of. So anytime that we would flip heads, we'll refer to this as heads, and anytime that we flip tails, we would refer to tails. So when we flip a coin, a macro, or not macro, micro state is a detailed description of every element in the system. So if I flip 5 times, let me see if I can get this to copy over. If I flip 5 times, there's some scenarios that can happen. So let me try to shrink this down. Yeah, it'd be this. Okay. So I could do 5 heads, 0 tails. I can do, let me spread it out this way, 4 heads, 1 tail. I could do 3 heads. This is if I flip a coin 5 times. 5 heads, 2 tails, or I'm sorry, 5 heads, 0 tails, 4 heads, 1 tail, 3 heads, or I'm sorry, 2, well, let me finish this before I get ahead of myself because I'm going to make it all weird. All right, so these are the scenarios, right? I could do 5 heads, 0 tails. So if I flip the coin 5 times, there is a high probability, not a high probability, there's a probability that I can have this sort of scenario happen. Let me zoom in on this. We'll make this 14. We'll make it 15, 16. And so a lot of times what we would do is we would denote this by what we call the macro state or micro state. So we would just write down one scenario, which would be heads, 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 4 H's for 4 heads. The next one would be heads, 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 4 heads, and then 1 tail. And then down here on the bottom, we would just have 5 tails. And I'm not going to write them all out. There's a table of this in the online textbook. Well, let's write them all out. What the heck? So we have 1 head, 4 tails. The tails are pretty easy to write. And then we have 2 heads, 3 tails. I've got it. 2, 3. Then we have 3 heads, 1, 2, 3, 2 tails. And so we would call this and there is such a thing as a macro state and a micro state. So the individual macro states are the combos that you would get. So, so this is one scenario. Let me try to give you another. So I'm going to try to copy this from, I'm just going to do this first one here. So when we consider 4 heads, and 1 tail, Well, I could have, the first time I flip it, I can have a head, then I can have a tail, then I can have the rest heads. That's one particular combo, right? Or the first time I flip, I can have tails and I can have 4 heads. Or I could do 2 heads and then a tail and then 2 heads. And so basically we're just moving the tail across. So I could have 3 heads a tail and then a head. And then the last combo would be 4 heads in a row and then a tail. So I have 1, 2, 3, 4, 5 microstates. So when we do the microstates, this would be 1. This works out to be 5 because this is the one I did the example. This would be 10 different scenarios. This would be 10 different scenarios. And then 5 and 1 again. And so, well, what does that have to do with anything? Well, there are actually, the macro state is, the macro state is the overall property of the system. So when we think about the system, this is, what's the system? I would take a coin, I flip it 5 times. So the macro state of 3 heads and 2 tails is achieved 10 different ways, right? Not surprisingly, is equally probable to do 2 heads and 5 tails. So what does this have to do with, well, we'll get to entropy in a second, but what I want to do is I want to show you just some possible scenarios of the number of macro states and if we flip things. So, and this whole table is posted in your book, but I just want to show you basically what we're talking about. So if I were to do the probability on this, the macro state of 100 heads and 0 tails, there's only 1 macro state, or micro state. If I have 99 heads and 1 tails, my total combination, and it would be like 99 heads, and then somewhere we would insert 1 tail. Well, the number of macro states for that one would be this number, okay? And then so on and so forth. Well, there's a pattern here. If I had 95 heads and 5 tails, where we place those 5 tails and then the other 95 heads, you would get this many microstates. And so how we calculate that is a matter of probability, but just know that this exists. So what does this have to do with entropy? Well, quantum mechanics kind of works the same way. We don't know how certain things are going to act, but we can analyze the possible combinations and the probabilities, and then what we try to do is make our calculations based on those probabilities. So even a small amount of gas has a huge number of atoms, right? So an ideal gas at 1 atmosphere and 0 degrees Celsius, let me write this down, and this is coming from the textbook. So if I, let's figure out how this will relate. So if I have, so there's disorder in gas, right? And so if I have 1 cubic centimeter of a gas, and it's at 1 atmosphere of pressure, and the temperature is 0 degrees Celsius. That's about 2.7 times 10 to the 19 atoms or particles. We'll just assume that's an element. Maybe it's helium, it doesn't matter. So that's about how many atoms we have. So then if that's the case, so each macrostate has an immense number of microstates. In plain language, that means that there is an immense number of ways that the atoms in the gas can be arranged while still having the same pressure, temperature, and so on. So let's look at what I'm talking about. Now, this is not 2.7 times 10 to the 19 atoms, but what they're talking about in the arrangement is like this, right? So, well, this is what we have to do all of our math on. So it's highly unlikely, right, that you're going to have all of them right here in the corner. Highly unlikely, but not impossible. More than likely, because of their kinetic energy, they're going to be kind of spread out, But as the temperature changes, this probability changes, right? So when the temperature is lower, you have less kinetic energy. The randomness of this also, by the way, this is a perfect rectangular container. What if the container in which the gas is contained in is not symmetrical or doesn't have some sort of order? That changes everything. Well, we have to change the way that we approach entropy and heat transfer in what we consider to be an ideal gas. Okay? So when we look at the ordinary state of the gas in the container, it's disorderly in the sense that they're not perfectly evenly distributed, but in the randomness of their distribution, there's a probability of where they might be. Okay? And so this random distribution of atoms or molecules with what we call a Max-Boltzmann's distribution of speeds, right? Because they're all going to have different speeds. That's what these little arrows mean, right? So this one isn't going as fast as this one. So that changes the position. Everything in the universe is dynamic. Nothing is sitting perfectly still. So everything's moving. So there's a certain number of randomness. But if you take and you average the things, it tends to be a little more organized, but that's where the probabilities come in. Now, when we get to B, the energy transfer of the gas can be forced into one corner, and its entropy will be greatly reduced, right? So we lose entropy here. So here our entropy, or our change in entropy, would be higher, and here, because the proximity of the molecules, because they're all kind of grouped together, our entropy will be less. So remember that delta S just means entropy. Well, we don't really know, right? Because we're going to use formulas to make predictions. And so, but we can calculate, we can make certain calculations. So one of the ways that we could approach entropy is if we have capital S, K, ln natural log of W, where K is Boltzmann's constant, right? 1.38 times 10 to the negative 23 joules per Kelvin. Ln is just the natural log, but W is the natural logarithmic number, where W is the number of microstates. And of course, ln is just natural log. Okay. And W is proportional to the probability of the macrostate that will occur. So the entropy is directly related to the probability of the state, and more likely the state the more likely the state, the greater the entropy. Okay? And so we use this a lot with regards to the second law of thermodynamics. So we're going to try to apply this to a coin toss at first, and then from there we're going to see how this works with a gas or an ideal gas. So let me throw a little problem up here, and then we'll try to do this in both scenarios. So the first thing I'm going to do is I've got this increase in coin toss. So suppose you toss 100 coins starting with 60 heads and 40 tails, and you'll get the most likely result is 50-50. What's the change in entropy? Okay, so to do this, we need to know a couple of things. One, let's do a little review. We said that the change in entropy is equal to the final entropy minus the initial entropy. And then we said that was Boltzmann's constant times the natural log of the microstate's final minus Boltzmann's constant times the natural log of the microstate's initial. So we've got to figure out the initial. So we've got to go. There's a formula. I'm going to try to find this for you. So the first. So we need 60 heads. This is the initial. 60 heads, comma 40 tails. And then we need 50 heads, 50 tails. So I'm gonna, on my other screen, I'm gonna pull up this table and see what numbers I get. So 50 heads, 50 tails. Let me take some screenshots here. So 50 heads and 50 tails. This just, when I went to the table of values, this just happened to be up there. And then I got to do 60 heads, 60 tails. 60 heads. There it is. So this is heads, this is tails. So then to find my change in entropy, I'm going to do Boltzmann's constant 1 times, and I'm going to factor that out. In other words, I'm going to do this. I'm going to say Boltzmann's constants times the natural log of the final number of macrostates minus the natural log of the initial. Okay, so let me get back to my screen here. So this will be times 10 to the negative 23. Oops, 23, not 3. I was going to write down 32. 23. And then based on our numbers, the final is this one, right? So I'm going to say 1 times 10 to the 29 minus, oh, and this is, I got to write the natural log. I'm going to run out of space here, I think. Um, let me do this. So this is a function, right? The natural log of 1 times 10 to the 29. That's a number, minus the natural log of 1.4 times 10 to the 28. Okay. And so if I plug that in a calculator, I get 2.7 times 10 to the negative 23 joules per kilogram, or Kelvin, sorry. And that was it. So that one's not that hard. Now, in this class, we're going to kind of rig up. If you were to do this at the graduate level in college, you would have to calculate these microstates. So this, just to recap, this is your possible outcomes, and then this is the microstate, which we're referring to as capital letter W. Okay? So what does that mean? Well, an increase in entropy means that we have moved to less orderly situations, right? It's not impossible to further toss us to produce the initial state of 60 heads, 40 tails, but it is less likely. There's about a 1 in 90% chance for that decrease in entropy to be negative 2.7 to occur. If we calculate the decrease in entropy to move to the most orderly state, we would get about negative 92 times 10 to the negative 23. So there's a 1 in 10 to the 30 chance, roughly. And so that's what we're talking about. This is a very, basically it would be 22 zeros, so it'd be decimal point followed by 22 zeros, 27. So it's a very small change in entropy, and so that's what we're trying to find, is the change in entropy. I mean, that's basically it. So the math on this is pretty easy, and then how does that relate to a gas? Well, you would do the same thing. Where the gas is binary. In other words, the molecule is in this location or not. And so it would be heads or tails, hit or miss, right? And so we could do the same thing to figure out what is the likeliness of this occurring versus the likeliness of this, and it's based on our change in entropy. So, and that's the relationship between the two of these. This is more likely to occur like this, but because of the randomness, how they're kind of spread out, and the variation of their velocities, the entropy would be higher. But if the entropy is very, very low, it's highly unlikely that we would do that, but it can happen. In other words, if I flip a coin 100 times, I can get 60 heads and 40 tails. But based on the entropy, that's very low compared to 50-50. Okay, and we're talking in terms of entropy, and that's basically it.